All right, big ideas, Algebra 2, Section 4.5, solving polynomials. So we're going to be able to find solutions of polynomial equations and the zeros of those polynomial functions, and then use the rational root theorem as kind of an expansion to synthetic division that we talked about previously. So solving a quadratic that's of a higher degree than 2, which becomes a polynomial. So this has a degree of 3. 2x to the third minus 12x squared plus 18x is a little bit different than solving a quadratic. So you're going to want to make sure that everything is set equal to 0. Then factoring as normal as you did in the last section. So taking that 2x out of everything in common, which is your GCF. You're left with a quadratic trinomial that you can factor using your AC method. So finding two numbers that multiply to equal 9, but add to equal 6. Those are -3 and -3. You can then use the zero product property and set each one of those things equal to 0, which is 2x equals 0, and x minus 3 squared equal to 0. So both of your x values are 0 or -3. So those are your roots or your zeros or your solutions, x equals 0 and x equals 3. That's where the graph crosses your x-axis. It crosses at x value of 0, and then it comes back either down or up again at x equals 3, and then continues on again to infinity. So you can check that using the graphing calculator. So notice how it's crossing at 0 and then -3 again, and then continuing on forever. So finding the zeros of a different function of a power of 4, and then again sketching that function. So this -2x to the 4 plus 16x squared minus 32. Make sure that that's set equal to 0, because that's what you're solving for. You're finding the zeros. You're going to take out your -2 as your GCF. And then this is a quadratic trinomial, even though you have an x to the 4th. You can kind of treat this as an x squared equation by finding two numbers that multiply to equal 16 but add to equal 8. And when you get those are perfect squares of -4. You set those together of your x squared minus 4 together both sides. Then you're going to take your difference of perfect squares for each one of those parentheses. You got x plus 2 and x minus 2 for both of your parentheses. Set all of those things with exponents to kind of combine them back together, because you have two x plus 2's and two x minus 2's. Because both of your factors of x plus 2 and x minus 2 are raised to an even power, the graph touches the x-axis at -2 and +2, but it does not continue in the same direction that it would go through. So if you look at it on your graph, that -2 and that +2, it kind of touches up there on the x-axis, and then it continues back in the opposite direction on both sides of both +2 and -2. We talked about previously with end behavior with that degree of 4, and you're going to have both in the same direction because it is a exponent of 4, and then because you have a negative out in front, they're going to be pointing down. So that's how you know what the end behavior of each of those left and right side of your zeros is equal to. So rational root theorem, you have a polynomial equation with integer coefficients, so whole numbers, whether they're positive or negative. Every rational solution, so it could be a fraction, is a ratio rational solution, so long as that function is equal to 0, has a following form of the factor of the constant term dividing by the factor of the leading coefficient. So your constant term is that last number by itself in your polynomial equation, and the leading coefficient is whatever is that first number being divided by. So you're always going to have integer coefficients that are equal to that based on your possible solutions. It's a good starting point to find your solutions of the polynomial. But in order to find the actual ones, you have to test those values to see if they're actual solutions of the equation. So we're going to test this rational root theorem to find all the real solutions of this x to the third minus 8x squared plus 11x plus 20. So we're going to use synthetic division to determine if this is easily factorable or not. So we're going to list all of the possible rational solutions of this polynomial equation. The leading coefficient is 1. That means the first number in front of your highest degree term is 1. The constant is 20. That's a number that's by itself. So the possible rational solutions of your polynomial equal to 0 are plus or minus 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, or 20 over 1. Those are all possible factors of your constant term that are being divided by your leading coefficient. So the number 1 on bottom is always the same on bottom because it is your leading term. Then each number on top depends on any possible factors, both positive and negative, of your constant term. So you're going to test those possible solutions using synthetic division until you have determined at least one solution. So we're going to test with positive 1 because that's 1 divided by 1. You use that in your synthetic division and you get a remainder of 24. So because it's not equal to 0, it's not a factor. We're going to move on to x equals negative 1, plugging that into your synthetic division of the exact same coefficients. Going through that process, you do get a remainder of 0. So x equals negative 1 is a solution, which means x plus 1 is a factor of this equation. So factor completely using this solution of an x plus 1 as your factor. You can take that x plus 1 out of your polynomial equation, and what's left over is your x squared minus 9x plus 20. That actually comes from all of your terms that's left over from your synthetic division. So this 1 negative 920 is what you get left over here from your other terms. Now, sometimes you're left with a very easy quadratic that you can then factor two numbers that multiply to equal 20 but add to equal negative 9. You get your negative 4 and your negative 5. Then you can set each one of those things equal to 0. Negative 1, positive 4, and positive 5 are all of your real solutions. Now, depending on, sometimes you may have to test all of these other numbers until you get a remainder of 0. Then you can factor that thing out and whatever is left over. Sometimes that can continue to be factored. Other times it cannot, and you may need to use either complete the square or the quadratic formula. But that's a good starting point to test for your rational root theorem. So let's do another one of a degree of 4. So all of your possible rational roots, again, all of your constant terms being divided by the possible factors of your leading coefficient. So your leading coefficient is 10. All of those factors are 1, 2, 5, and 10. And then your last term, your constant, is a 12. So that's where you get your 1, 2, 3, 4, 6, and 12. Again, you have to make sure that they're both positive and negative. So even though there are a lot of possible solutions, you only need to test this until you get one solution to kind of help simplify it down from there. So choose a reasonable value. Don't make this more difficult than it needs to be. Start with a positive 1, then go to negative 1. Then start with a positive 2, then a negative 2. Don't use 3 over 5, positive or negative. Don't use 6 over 5. That's really hard to do with synthetic division. Choose real numbers. And then if you're still not getting anything, then you can move to those more complex numbers to determine your zeros or for your f values. So negative 3 over 2, negative 1 over 2, and 3 over 5, and 12 over 5 are all reasonable based on plugging this into Desmos or your graphing calculator, because that's where those could possibly cross in your window of your function between negative 5 and positive 5. So you can test some of those values until a 0 is found. Again, it's just kind of a guess and check type of system. So we're testing first negative 3 over 2. Notice a remainder is not 0, so you're going to continue on. Negative 1 over 2 does give you a 0. So this is a correct factor. So x plus 1/2 is a binomial that you could factor out of this. Again, you're going to want to keep continuing with this because it is a degree of 3. So take that 2 out. Then you're going to need to multiply by that factor of sliding over to the left-hand side so that you're not getting any more fractions. Rational root theorem again. Again, this is a very tedious process, but in order to determine all of your possible solutions, you need to be able to look at your constant term and your leading coefficient term that are being divided. So you could look at a 3/5 based on the graph. That could possibly be a solution. So when you use your synthetic division, it is a 0 of 3/5. You're then left over with an x squared minus x minus 4 of your term. You then can factor that, setting it equal to 0 using your quadratic formula. And you get your 1 plus or minus the square root of 17/2. So all of the real zeros are -1/2, 3/5, 1 plus or minus the square root of 17/2. And if it needs to be simplified down separately, you get your 2.56 and your -1.56.